Hello, I am Sheikh Jahiruddin. Once again, I have come with a new video in which I will be discussing the Part C questions of CSIR NET December 2019 paper. So the first question was that muon question, which was discussed heavily in the group. The concept is the effective mass concept, but the only issue is in that CSIR NET paper in the very small time that this answer is what was helium was not very easy to conclude with. So in that case, I would say that well, you might have done it wrong, no issues. But the concept, the effective mass concept was the basic concept that you need to replace the effective mass, which was 1 by 1836, 1 plus 1 by 1836 for the general mere hydrogen and proton, this proton and electron problem. So what I like to say is that effective mass, which was in the energy, I'm sorry, the size was of the pen was too large. So which was actually the eraser is coming. So this 1 plus 1 by 1836 kind of this factor was there in the general muon proton question. So this proton, if you had proton and electron, so for this factor was there, and if you have something say m1 here, m2 there, m2 orbiting, actually this is the effective mass concept. So for here you need to do with this 1 plus your m2 by m1. If your m2 and m1 are comparable, then you include this factor. So well, we will proceed. We will delete these things. This is a new style of teaching I have I am experimenting with. So well, this question was also a little bit tough, not very tough I would say, but you might have skipped this, so that is not an issue. I will say the easy questions, I will tell you that how easy it was. So here that this question was from Raman scattering and Rayleigh scattering. The Stokes and anti-Stokes, you know, right? That which is greater. I mean, Stokes and anti-Stokes you can compare. You know that the Stokes lines are most intense than the anti-Stokes line. So Stokes is more intense than anti-Stokes line, will always be there in option 1, in option 2, in this 2 option only. The Stokes is higher in intensity than anti-Stokes. But where would you place the Rayleigh scattering? Right, the Rayleigh scattering is the common scattering. Means in electrodynamics you read the radiation chapter, that is Rayleigh scattering, same frequency. But here in this Stokes and anti-Stokes, Raman scattering. Raman is always faint, right? That's why the Raman scattering has been discovered at when 1930, and Rayleigh scattering. All these were, we all knew all these things. So Rayleigh is the common, the same frequency line is Rayleigh, and the frequency where it differs, that is this Stokes and anti-Stokes Raman. So Rayleigh scattering is higher intense than Raman scattering, so there is no problem in that. This question 4 was also you need to integrate. So integration should have been done, but only problem is your kinetic energy factor was very easy, but the potential energy factor was not quite easy, because dq1 dq2 you need to integrate e to the power q1 square q2 square plus 1/4 of q1 plus q1 and q2. What you could have done is two ways. You could have changed the variable, just rotating the coordinates little bit, or you could have make it a whole square form and then change the variable. The variable change was necessary. The quadratic form. Did you ever heard quadratic form? And so these variable changes are not very tough. So this is kind of k 1/8 k 1/8 k. Then you change the variable. So if you did not know that type of integration, then I would say that you first read the quadratic form, coordinate transformation in the integration, then you will be able to do that question. So even you could have not done this question also in the exam hall, that should not be that could have been forgiven. So well, this whole coefficient and whole part, if you knew exactly what how the whole coefficient varies when the whole resistance varies with temperature, then you did. Or if you did not know, then you could not. So well, leave it for a just particular type of question. This was very easy, so I didn't know why you could not do. T less than d by temperature of copper, so temperature dependence. So when the much less than d by temperature dependence of specific heat, what specific heat? Lattice specific heat, lattice vibration, that is TQ. So this is lattice vibration, but did you, in the question it is mentioned that only lattice vibration? No, the temperature dependence of specific heat. So the lattice contribution will be there, and what another part is, another part will be electronic contribution. Your copper will have both lattice and means nucleus and electrons both. So for that, what you need to see is, this is the TQ part is your, this is this TQ, this TQ is for lattice, and your this part is for electron. This is electronic. So TQ is for lattice and this is for electronic. So if you did not read this, if you could not do, then it is very sorry. Well, we'll go to next. This is not very tough question. This is a calculation of critical coefficients. So critical coefficients, this Tc, rho c, Tc, all this from that equation of state. So if you know, but if you someday or in some point of your life in van der Waals gas, if you have really done that, so then you could have really done this also. So what else in van der Waals, what you did in van der Waals, oh sorry, always this is coming, sorry. So in van der Waals, that was P equals to KT by V minus B minus A by V square kind of thing. You did del P del V 0 square P in PV diagram del V square equals to 0. Then you made all these things, right? Critical coefficients. But here also the same things will do. Here you will see del P del rho, where rho is the variable 0, and you make del square p del rho square equals to 0. This will give you critical coefficients. Well, if you could not, then you lose. So we'll proceed. This is a generator of infinitesimal canonical transformation. If you never ever read this infinitesimal canonical transformation in your book, preferably from Goldstein, then you could not. But if you did, if you read, then you could. And suppose you didn't read, the generator of infinitesimal canonical. Do you know what generator is? So this is the transformation from this q to this just epsilon q. Q is changing to epsilon q, and this your p dash is changing to minus epsilon p. So then you just apply the formula. Well, so just a minute. This is the formula. If you don't know, then you could not. So I always tell you people to read this. So this is just if your f2 type of generating function is qp plus epsilon g, so then del p will be minus epsilon del g del q equals to epsilon del g del p. So this qp is contact transformation. This is just transferring from q to just q, not changing anything this part, and this epsilon g is changing this part, just changing from q to actually q plus epsilon q. So for that, the change of delta p equals to epsilon delta g delta q, and this is what delta p is minus epsilon p, and this delta q is the change of delta q equals to epsilon q. And can you get g, the generator of that transformation from now? So del g del q is p, del g del p is q. So then what option comes? Done. As simple as that. Well, we'll remove and we'll proceed. This is interesting, right? This PDF file here, this PDF file, and we can use this PDF file itself as a black whiteboard. Technology triumphs, man. This outermost cell of an atom and element is 3dq. The spectral symbol is very easy. Just easily you can do this. Nothing special, nothing extraordinary. We'll proceed. This is electronics, and I think I am not that much of capable to handle that question. So if you could not, then fine. Here this you might have done well if just do the derivative, get the answer, but that will need some more time. This is time consuming. If you theoretically do that derivative, make it 0 for most stable ratio, but don't you know the formula, right? For most stable z, you don't know. You should always. Most stable z is a mass number by 2 plus 0.015 approximately a to the power 2 by third. Apply it, you are done. If you don't, you will spend 10 minutes time, then you might have a calculation mistake, then at the end of the day you lose 6 marks and you lose another 10-15 marks due to your spending of time and lose of confidence. So then that was very easy. I think every people have done that. This have also created confusion that what is that k? This is the wave number of that electromagnetic wave, and where this k, this electromagnetic wave k is outside of your waveguide, because you're saying that you have an electromagnetic wave excited by wave number k, your that k is the outside k, and that group velocity, what group velocity mode is, you read Griffiths, the waveguide from Griffiths. This is can be done. This is also transistor biasing. This is very easy. I think even myself also could do that. Transistor biasing, you must know what transistor is, how this is biased. This is a DC biasing also, what beta is, what alpha is. This thing also is not a problem on that. This is Doppler width of optical line. If you don't know what optical line means, what the Doppler broadening is in atomic physics, then you could be forgiven for that. So this is easily okay. If you didn't, then you didn't. You know. Decay. Which of the following decay process is allowed? Well, you say, sir, we are conservation numbers. We are just saying what conservation numbers are allowed. What conservation number नहीं मिल रहा है, conservation number ये हो रहा है, वो हो रहा है, ये हो रहा है. Well, be little bit mature. Try to identify what kind of problems this, what type of reaction is this. If neutron decays, it will have a neutrino, right? Neutron decays with a neutrino. Neutron never decays like this. Neutron always decays proton plus, not pi meson. This decays with positron. Sorry, electron, proton plus electron neutrino. So conservation number you can apply, but this reaction does not happen at all. Neutrino will be there. Where do your neutrino was? Lepton number conservation and not here. Baryon number conservation and not here. So very easy, all these things. Muon decays in electrons and this gamma photon, where the conservation number of electron neutrino and muon neutrino separately, lepton numbers conserve separately. If his muon is there, there should be a muon neutrino here. If electron is there, anti-electron neutrino would be there. No neutrino. So what left? This is always happen also. K meson decays in muon, mu plus and mu minus. So mu plus, mu minus, no mesonic, no leptonic conservation number is necessary, because this muonic destroys baryon numeric conservation. Where is your baryon number? This is not a baryon, right? This is meson. So mesons decay in leptons. No problem. This also can be left. This is random walk, man. Random walk, you know the average is n multiplied by p. So the probability multiplied by the total number of samples is the average displacement or average propagation of that variable. So you just the x side that's much displacement, y side that's much displacement. So then you just add. Hopping is 0.3, negative x direction is 0.2, positive y 0.2, negative y is 0.3. So effectively positive x is 0.1, negative x is 0.1. So positive x 0.1, negative x 0.1. Fine. This is positive x 0.1. This is negative y. This is saying 0.1 mean. So the effective displacement will be n, the direction will be y minus j. What else? The mean position, right? So how much steps it has taken? N steps. So n steps, position is this. And what is the unit? The unit is 1 by 10. So your this 0.1 and 0.1 I 0.1j, that 0.1 comes in your answer as 1 by 10. So this is no issues. We'll proceed. We'll delete our blackboard. Well, this cos square phi, you need to write it in terms of YLM. Then you can do this answer. So you need to know what YLM is. You need to express this as your YLM. Then you can do this Josephson junction. If you have read Kittel ever once in your life properly, then you know the answer. The Josephson junction, this is Josephson junction. This is your answer. Fine. This is class 11 student can do, right? Dimensional analysis. So this is dimensional analysis. You perform the dimensional analysis as you have studied in class 12. Then fine. This is the properties of radiation. If you ever read radiation, what properties are, then you can do. So discussing this is wasting of time. It's just know what the basic properties, basic results of your radiation. If you could not, then you have a blunder. You need to know every basic things, right? Very small things. So that is done. This can also be done. You might have do a mistake in doing the calculation, but it could be done. The percentage error estimation. If you could not also, okay, this can also be forgiven that you made a mistake. This is a nonlinear dynamics, a proper nonlinear dynamics question. I I don't expect that very few people have done that. Who have some special knowledge or some special course in their masters, then they could, otherwise leave it. This is also beyond of my knowledge, I guess. Not beyond my, your knowledge is well, fine. But electronics I leave generally. This is Fourier series. If you know what Fourier series is, how the Fourier series can be solved, then fine. This could also be done, not very tough. David Griffiths problems, David Griffiths type of problem. The bound surface charge. You know what bound surface charge is, right? If you don't know what bound surface charge is, then I cannot help you, right? Hamiltonian is given this function is constant of motion only if this function commutes with that Hamiltonian. So commute means here the Poisson bracket. This is the classical thing. So the Poisson bracket of that function, if Poisson bracket of your this f with h is 0, then this is your constant of motion. Then this function is constant of motion. So then if you don't know, then I cannot help much. But well, this is, if anything is, if your any function commutes with h, this is not explicitly time dependent, so this means your f is constant. So just apply this is your f, so make it not an issue. Well, this is the calculation of an average value, right? Psi h square psi. Then expectation value is h square average minus h average square. So that's easy. This is the basic diffraction formula that you have studied in your BSc. This most of the people will do wrong, because most of the people will take the answer here. But this actually shift your x. This is not your ij. This is not wave function. This is x vector. So this operator actually shifts your x vector from x to x plus a, but that does not mean that the eigenvalue becomes x plus a. Rather, that eigenvalue becomes this x minus a. Surajit sir have explained it very clearly and posted that answer. So if you're confused, then consult Surajit sir's answer. Some had posted in all the groups, or read Sakurai. In Sakurai, where this operators, the ship translation operator has been discussed, chapter 2, quantum dynamics, Sakurai, then you're able to understand. So let us finish this video today right here. I'll be again come back to discussing something, and I will always be with you. So thank you for watching that video. Thank you very much.